Hello, I'm Seema and welcome to part 10 of the chapter Alcohols, Phenols and Ethers. This is part 4 of the series in which I have been doing the topic preparation of alcohols. In the previous 3 videos, we discussed the different sources from which alcohols can be prepared. That is from alkenes, from carbonyl compounds and from Grignard reagents. In this video, I intend to do the question 11.2. It is an example in your textbook, and the reason I want to do it is that by doing this question we will kind of mostly revise most of this topic. So that is the intention. In the question, you're only supposed to give the names of the products, the IUPAC names of the products, but I have intentionally written down the equations so that we can, the intention is to revise. So let us start with the question. Give the structures and IUPAC names of the products expected from the following reactions. The first is catalytic reduction of butanol. We know aldehydes and ketones can be reduced with the help of catalyst. The catalyst can be nickel, platinum or palladium, and they yield alcohols. You can also use reducing agents like lithium aluminum hydride or sodium borohydride to carry out this reaction. We have done the mechanisms of this reaction and I have explained this to you. So we will just see what is the product here that we formed. When you carry out the catalytic reduction of butanol, write down the formula of butanol. Butanol would have 4 carbon atoms. Al means it is an aldehyde. So aldehyde is a terminal group. It means it is a group which is always seen on the last or the first carbon atom. It is never, aldehyde is never in between the chain. So CH3, CH2, CH2, CHO. The compound should have 4 carbons. It is butanol. It should have a CHO is the functional group and it should be on the last or the first carbon. So this is butanol. You are carrying out the reduction. Reduction means addition of hydrogen. And in the presence of a catalyst, we are using palladium here. And what will happen? You will get an alcohol. The hydrogen will add, and in this case, the carbonyl group which is present, you know how the carbonyl group is? It is C double bond O. And when hydrogen adds to it, HH, this bond breaks. The 2 hydrogens get their electron, 1 bond breaks, and these 2 carbons get their electrons. 1 hydrogen attaches itself here for giving you an H here, and 1 hydrogen attaches itself to the oxygen, making it an alcohol. Instead of CHO, you now have COH or CH2OH, whatever the compound is. So let me just rub this off and see the compound again. So we have butanol. Hydrogen adds to it in the presence of palladium. It results in the formation of this compound CH3, CH2, CH2, here CH. So 1 hydrogen adds to carbon, so it becomes CH2, and 1 hydrogen adds to oxygen, so you get OH. So this is the structure, and how would you name this compound? It would be butan-1-ol. The IUPAC name is that it is butanol. And since the ol or the alcoholic group is attached to the first carbon, we will count from this direction so as it gets the lowest locant. So it is butan-1-ol. The second part, you have to write the product of hydration of propene in the presence of dilute sulfuric acid. We call it acid catalyzed hydration, and acid catalyzed hydration of alkenes takes place in order to give you alcohols. So acid catalyzed hydration of acid catalyzed, the catalyst is an acid, hydration means addition of water molecule. Just as reduction is addition of hydrogen, hydration is addition of a water molecule. So you have an alkene to an alkene, a water molecule is added in such a way that the, let's just come here, or let me just write it down because I have not written a single, just the overall reaction. So alkene is like C double bond C, this is an alkene. These are all hydrogens or methyl groups or whatever. Plus H2O. H2O is HOH. So this breaks here to form H and OH, right? This gets its electron, the oxygen gets its electron, and the bond here breaks, one gets attached here, one gets attached here. So you get CH3, CH2OH. So that is how you will get an alcohol. This is the overall reaction that is going to take place. Let me remind you that this was a reaction in which Markovnikov addition takes place. The addition that takes place is Markovnikov addition, which means in water the negative part is OH, so the negative part of the addendum will always get attached to that carbon which has lesser number of hydrogens already. We'll come to that later. Let us first see the steps. What are the steps of this reaction? And we know that Markovnikov addition is going to take place, and the addition is of water. Wherever the double bond breaks, one carbon is going to get hydrogen, the other one is going to get OH, and it will turn into an alcohol. So, since it is a Markovnikov addition, you should know the mechanism. In the first step, an electrophilic addition takes place. So, protonation of propene. Protonation takes place, which is an electrophilic attack. For protonation to occur or for an electrophilic attack, you should have a positive species, that is, you should have an electrophile. So how is the electrophile made? Water is the reactant, because what is adding is water. So, and acid, H positive, acid is a catalyst. So the catalyst, it attaches itself to the water molecule and turns it into hydronium ion. When it turns it into hydronium ion, the hydronium ion is positively charged, therefore it is electrophilic in nature. So generation of the electrophile takes place first. What is happening? Oxygen, in water molecule, oxygen has two lone pairs of electrons. H positive has positive charge. So one of the lone pairs is given by oxygen to form a covalent, or we call it a coordinate bond, with hydrogen. So it forms a bond with hydrogen. So now oxygen is left with only one lone pair, and in a covalent bond, both oxygen and hydrogen should have contributed one electron each. But oxygen is contributing both the electrons, therefore the positive charge now shifts to oxygen. Instead of hydrogen, hydrogen now got the electron, therefore the positive charge is neutralized. But since oxygen lost one electron, it actually gives two electrons in the bond, but one electron still belongs to it. The other electron is now taken up by hydrogen. So oxygen becomes positively charged, thus the electrophile hydronium ion is generated. Now we come to the first step, attack of the hydronium ion or the proton. The proton does not attack directly, it first forms the hydronium ion and then it attacks the alkene. Which is the alkene? We have propene. So here is our other reactant, propene. You have propene, hydronium ion attacks it. So what happens? As soon as the hydronium ion comes in contact with propene, the double bond here has, or the second bond or the pi bond between the two carbons is very weak. So it has a tendency to be loose. Those electrons are easily available for reaction. So what happens? Oxygen says is more electronegative. So it says, look, I gave you my electron and I want to take it back. So oxygen takes back its electron, therefore hydrogen again becomes H positive, but oxygen, when it gets back its both the lone pair of electrons, one electron already belonged to oxygen, the other it had given to hydrogen, so it gets it back and therefore the positive charge gets discharged or it becomes neutral. But H positive is separated and water molecule is separated out. So water molecule is separated out, which is now neutral. Right? And what happens to the H positive? The H positive which was created, the lone pair of the pi electrons from the double bond, they are provided to this hydrogen. Now, how was the pi bond formed? The pi bond was formed by the contribution of one electron from each carbon atom. Here is where Markovnikov's addition starts. You start noticing why Markovnikov addition. According to Markovnikov rule, the negative part of the addendum adds to that carbon which has less number of hydrogens. and the positive part automatically attaches to that carbon which has more number of hydrogens. And hydrogen H positive is positive. So where will H positive attack? It will attack that carbon which already has larger number of hydrogens. This carbon has only one hydrogen, but this carbon is attached to two hydrogens. So the hydrogen ion which comes will come and attach itself to this carbon. And that is what happens. This carbon now has three hydrogens attached to it, but this carbon is contributing its electron in the formation of the bond with hydrogen for the other atom. Therefore, this carbon now acquires a positive charge, thus leading to the formation of a carbocation. This is a carbocation that is formed. And why does the hydrogen attack the carbon here? Why is the secondary carbocation created? If the hydrogen ion would have attached itself here, the positive charge would have come on the first carbon, it would have been a primary carbocation. But it attaches, the hydrogen ion attaches itself here to give the positive charge to the second carbon, making it a secondary carbocation. And we know that secondary carbocations are more stable than primary carbocations. Therefore, this reaction is favored naturally. It is not like Markovnikov was so great. He said, okay, so you are going to go, negative part will go and add there and positive part will go and add there. No, he was the one who, for whom this trend has been named. But the reason for this trend is not an order by Markovnikov. This is what he observed, and that is why it is called Markovnikov addition. So what happens? It gives you this addition of the hydrogen ion yields a secondary carbocation. In the next step, a nucleophilic attack of water takes place on the carbocation. Now the water molecule, the positive charge is on this carbon, and water molecule, as I told you, oxygen has lone pairs of electrons. They are also available for participating in reaction. So water says, okay, let me participate. So oxygen gives one lone pair of electrons to this carbon and attaches itself here. So the entire water molecule gets attached to this carbon, but as soon as oxygen gives both of its electrons to form the bond, oxygen now becomes positively charged. So water molecule adds here where the positive charge is at oxygen. Now oxygen has only one lone pair of electrons, and the positive charge has shifted to oxygen because carbon is no longer positively charged. It is neutral. It got one electron. It had one positive charge, one electron. It's neutral. But oxygen now is deficient in one electron. Whenever you have a charged particle, it is not stable. So this cannot be the final product. The final product will have to be a stable molecule. This is still very reactive. So what happens? Instead of such a huge molecule, hydrogen says hydrogen is little and it has a pretty strong tendency to lose its electron and just move away from the compound. And that's what the hydrogen does. But it doesn't do it on its own. It does it again with the help of a water molecule. So deprotonation. Hydrogen leaves in the form of a proton. Why do we say proton? Because hydrogen atom has only one electron and one proton. If you remove the electron, hydrogen is reduced to only the nucleus having only one proton. So we call it deprotonation. H positive is also called only a proton because it doesn't have electrons. So deprotonation occurs of the compound, of this ion, and that gives you the alcohol. So what happens? The hydrogen here decides, okay, I'm leaving without this electron. So it leaves as H positive. It gives both the electrons. One electron was of oxygen, the other electron was of hydrogen, but hydrogen loses its electron, forms H positive, and oxygen gets back both of its lone pairs. Sorry, here. Oxygen gets back both of its lone pairs here. Okay? And the H positive which leaves, it goes and attaches the lone pair of electrons on oxygen in a water molecule. They provide the electrons for hydrogen to pull out the hydrogen in the form of H positive. And that H positive forms a bond with this oxygen with the help of the 2 electrons of oxygen, thereby making the oxygen positively charged. So it regenerates the hydronium ion which was produced. And that is the reason why we call it acid catalyzed. Here you see the H positive which was added in the beginning in the form of H3O positive. In the end, it is removed as H3O positive. So the H positive act as, or the acid acted as the catalyst. But what actually happened? What has added? H on one carbon, and OH, H on one carbon, and OH on the other carbon has added to give you a secondary alcohol. And that is why it is Markovnikov addition. So what does the question say? You have to write the structure. The structure is here. You could condense it also and give the IUPAC name of the product. So what is the name of this product? It would be propan-2-ol, right? Propan-2-ol will be the IUPAC name of this compound. Here, sorry, that is the positively charged one. Now comes the third part of the question. You have to give the name of the product, IUPAC name of the product, and the structure which is formed as a result of a reaction of propanone. Propanone is a ketone with methyl magnesium bromide. Methyl is alkyl group R, Mg, X, halogen. So it is a Grignard reagent, right? The reaction of a ketone with Grignard reagents also gives you alcohol. So how does it happen? You know, Grignard reagents are highly reactive with water. They can cause the formation of the original, hydrocarbon if they react with any compound, if they come in contact with a ketone or an aldehyde. But so what do? The reaction of propanone, in the first step, we do not allow water to come close to it. We just take the ketone and we make it react with Grignard reagent, and it results in the formation of an adduct or an intermediate. This adduct is formed by the addition of Grignard reagent to the ketone. So what is the ketone? Propanone. What will be the structure of propanone? Propanone is CH3COCH3. Propane, 3 carbons. So CH3CO, CH3 is propanone, CH3MgBr is methyl magnesium bromide. What happens? The bond here breaks. Magnesium gives its electron to CH3 and the bond here breaks. The CH3 comes and attaches itself to carbon, and magnesium attaches itself. Magnesium is more electropositive, oxygen is more electronegative. So magnesium attaches itself to the oxygen here. So you get CH3, the CH3 comes here. So see, this carbon is now attached to 3 CH3s. 2 were originally there. Third one comes, so there are 3 CH3s, and the double bond is broken. There is a single bond with oxygen, and MgBr, sorry, I wrote X. MgBr attaches itself here. Bromide, right? So here also it should be bromine. So MgBr attaches itself. This is the adduct that is formed. Now we add water and the hydrolysis takes place. So when you add water, the hydrolysis means breaking down of the molecule with the help of water. Water breaks into H positive, OH negative. So, or H and OH. So the H comes and attaches itself to the bond here breaks. The bond now again breaks between oxygen and magnesium, and water is HOH, breaks down. The H comes and attaches itself to oxygen, resulting in the formation of the alcohol, and the OH gets attached to magnesium, thereby forming MgOH-Br. So these are the products. So what is the name of this alcohol now? What is the longest carbon chain that you have? 1, 2, 3. It has 3 carbon atoms. And this becomes a branch. So this is propan, and this is a branch. So it is 2-methyl propan 2-ol. would be the name of the compound. 2-methyl-propan-2-ol would be the name of the compound, and this is the structure of the compound that will be formed. So with this, we finish this topic, that is preparation of alcohols. In the next video, we'll be taking up preparation of phenols. So if you wish to watch other videos of this chapter, please click the link that appears on top of the video. If you found this video helpful, give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching. Bye-bye for now.